Now, we will going to take up one more case on simply supported beam, having draw the SFD and BMD for a simply supported beam carrying uniformly varying load from 0 at each end and W per unit length at the center. So the center is here, which is W per unit length, and this is the span of length L, and here the height. So 0 at each end, 0 at A and also 0 at B, and the height at the midspan is W. So this is a figure shows a simply supported beam capital AB of span length L carrying a triangular load. So the support reactions will be support reactions is what is the total load on the beam? The total load on the beam will be equal to area of the load diagram. So what is the area of the load diagram? So that is a triangular load wherein you have half into base into height. Half into base is L, height is W. That is half into W into L. So since by symmetry, the reactions at the support A will be equal to reactions at the support B. So that will be equal to half into base into height that divided by 2. So that means half into W into L by 2. So that will be equal to WL by 4. Therefore, RAV will be equal to RBV, which will be equal to WL by 4. Now we will go for the shear force and bending moment diagram. So to find out this, consider a section XX at a distance x from A between A and C. When you are considering the section between A and C, so when you are considering between the section A and C, here from the similar triangles, we have ACW and AXX. So that will be equal to, suppose if you are considering the smaller triangle, XX by small x will be equal to W by L by 2. So we want this XX. So what happens? W into X by L by 2. So that is the height of this. So section shear force at section XX will be equal to RAV minus half into base is X, half into base is X, into height is W into X by L by 2. When you cancel these two, so then L by 2 and this half will going to be get cancels. So we will going to get it as Wx square by L. So that means that will be equal to W into L by 4 minus W into X square by L. Call this equation as 1. So from the equation 1, it shows that the shear force varies according to the equation of a parabola. So that is, when you are joining between the 2 points, you have to join by means of a parabolic curve. So that is the meaning of this. So when the value of x is equal to 0, SF at A will be equal to W into L by 4. Substitute the value of x is equal to 0 here. So you are going to get plus WL by 4. Similarly, when the value of x is equal to L by 2, so what happens? W into L by 4 minus W into L square by 4 by L. So that means W into L by 4 minus W into L by 4 equal to 0. Similarly, considering the section between B and C, if you are considering, so again SF at B will be equal to minus WL by 4. Applying the same concept, you are going to get the same value with a negative sign. So similarly, now when you are considering the bending moment at the point section XX, so that will be equal to RAV into X minus half into W into X by L by 2 into X, that is the base, and that is the half into area of the load diagram. So area of the load diagram is half into W into X by L by 2, that is the height, into the base is X, and the distance of center of gravity from the section at XX from the bigger end will be X by 3, so into X by 3. So 2 gets cancelled, so that will be equal to here RAV, which is WL by 4 into X minus WX cube by 3. So half into W into L by 4 into X minus WX cube by 3L. So once you get this, so that will be call this equation as 2. So once you get this equation, so from the equation 2, it shows that the bending moment varies according to the cubic law. So here, according to the cubic law, once you get this, the maximum bending moment occurs at a point where the SF changes its sign. So that is maximum bending moment is at the point C. So when the value of x is equal to L by 2, what will going to be the bending moment? So x, put the value of x is equal to L by 2. So that means you will going to get W into L by 2 by 4. So minus W by 3L into L by 2 means L cube by 8. So therefore, W into L square by 8 minus W into L square by 24. On simplification, you will going to get it as W into L square by 12. So similarly, considering a section between B and C, Bm at the point B will be equal to 0. So therefore, the maximum bending moment will going to be at the point C, wherein you are going to have W into L square by 12. When you plot the considering the values of both the shear force and the bending moment diagram. So when the value of SF at A is plus WL by 4, you are going to get this point here. And the value of SF at the point B will be equal to minus WL by 4. You will going to get this point here. When the value of SF at the point C, it will going to become 0. So join these 3 points by means of a smooth curve by passing through by these 3 points by a parabolic curve. So this is how you will be able to plot the shear force diagram. And similarly, when you want to do the bending moment diagram, so bending moment at the point A is 0 and the bending moment at the point B is 0 and the bending moment at the point C will be equal to W into L square by 12. So join these 3 points by means of a smooth curve by using a cubic curve, because in the bending moment equation, the power of x will be equal to 3. So therefore, you will going to get the bending moment diagram in a cubic curve. So as we see from the diagram, that when the value of the shear force changes its sign from positive to negative, the value becomes 0 at this point. So at that point, the bending moment will going to be the maximum, which will be WL square by 12. So this is how you will be able to analyze and solve the problem on the uniformly variable load on either side by taking at the midspan the maximum at W, at the either ends it will be equal to 0. If you find this video is useful, please subscribe to my channel. Thank you.